already listened to this talk, but at least you will get the last update and the status of the project. So this work has been done in cooperation with my colleague Jean-Daniel Reddy, together with Hassan Henrik and Peter Monkewitz from APFL, and I would say direct and indirect help of other people. So I think we are convinced. I mean, this program is confirming that there are still controversies and uncertainties on many fundamental issues: so large-scale structures, universality or non-universality of carbon constant, scaling, probe resolution. So I think we all agree that we need to study high Reynolds number flows, we need to resolve all turbulent scales, and we need, of course, web converged statistics. As my colleague Jean-Daniel showed in the early part of the program, there are, we can use, of course, several tools. Direct numerical simulation has a quite good resolution, good statistics, but still, we think, too low Reynolds number. Beverly showed us experiments in the Utah, so in the Salt Lake Desert, with a quite high Reynolds number, I would say quite good resolution, but probably not enough converged statistics. So we still have to rely on laboratory experiments where we can reach high Reynolds number, quite good statistics, but the point is we need how to have enough resolution. So first of all, how we can increase the Reynolds number? Well, we know that in SuperPipe in Princeton, you can reach high Reynolds number by playing with the density. There are other attempts, of course, at CERN, U2Shea group, that are, of course, using cryogenic flows, so they can lower the viscosity. With this type of facilities, you can get very high, well, I would say high Reynolds number, up to 40 billions. But of course, what you get is you have to deal with very small viscous landscape. So this motivated us, and in trying to find a kind of new experiments. But first of all, we want high Reynolds number, but how much high Reynolds number? What is the minimum Reynolds number that we have to reach? So if we believe that the logarithmic region starts at y plus 200 and finish at 0.15 R plus, we're talking about 5 flows, then if we want at least one decade of y plus to study, we have to end up to a y plus equal to 1000. So in this case, we end up to an R plus of 13,300. And if we want to play a little bit with the Reynolds number to do so, we need to try some scaling, and we say that we want to go up to 3 times the minimum Reynolds number, then we see that this is the range that we have to get with our new experiments. Then, of course, there are other data that suggest that probably the logarithmic region starts slightly afterwards. So in this case, we have to, of course, increase these numbers. Now, when it comes to small-scale resolution, and Ivan in his talk explained us quite well, which will be the problem. We believe that the minimum diameter of the wire that we can use is 0.6 micron, even though, technically speaking, it's quite difficult both to solve and to keep alive. And if we still believe that we need an L over D more than 200 in order to avoid heat conduction, we can lower this value a little bit if we use different material, but we want to stick to things that are already existing. So we end up to a wire length that is slightly more than 120 microns. Now, again, probe resolution. So we saw that we need, if we want to be on the safe side, L plus should be less than 10. So if we want to have this one, then we end up that we can only measure these scales which are larger than 12 micron with this, let's say, standard techniques. Well, this is just an example how that show that L plus equal to 10 can be maybe, you can see enough to detect, for instance, the intensity of the peak of the standard fluctuation. So, it's easy to show that actually the viscous scale is equal to the ratio between the pipe, we are still referring to the pipe diameter and L plus. So it's equal to the ratio between the radius and the Reynolds number. Then, if we want to keep this number, if we want to keep L plus more than a certain number, and if we want to go up to a certain Reynolds number, we can see from here that we can only play with the physical dimension of the facility, with the radius. So, if we plug in our numbers, L plus should be more than 12, R plus 40,000, we end up to a pipe which has a radius of 0.48 meters. So, why a large facility, now why a long facility? Well, we had a very nice discussion with Basil a few days ago, but our idea, the philosophy that is motivating us is, well, to define an experiment that can be used for any type. So we really want also to test fully natural developed turbulent flow. So if we stick to this, let's say, thumb rule, which is recently confirmed in measurements by Jason in Melbourne, we have a facility which has to be at least 100 meters long. When it comes to accuracy of this pipe, if we take data from the NDF and MTL, where we want to limit the variation in velocity to 0.2%, and we apply the same to the pipe, we end up actually to a maximum diameter variation of less than 1 millimeter. Remember, the number 5 is 90 centimeters. So a variation which is 0.1% in diameter. For as far as roughness is concerned, if you take Zagarola and Smith hydrodynamic smooth surface, they state that KS plus should be less than 3, so the roughness should be less than 3 viscous length. So for this is our root mean square roughness that we have to that limit this experiment. This is a value that it's not really a big deal. We will see it can be reached with most of the techniques available. But why a pipe? Well, also Hassan stressed this in the early days of the program. If we have a channel flow, of course we need to have a minimum aspect ratio to guarantee that the effects of the side walls are limited. So if we take, this is not a large value, but what we think is a minimum value, then we end up to an area ratio between the channel and the pipe of at least 10. So we have a quite higher flow rate. Moreover, in the channel, we know that we need an independent measure of the wall shear stress, which makes it more complicated. So this was the new experiment that came out from several workshops in Princeton and Trieste in 2004. So this facility, we said it should be a pipe flow. It has to be closed in order to control all the parameters. It has to be at atmospheric pressure in order to have easy access. The diameter should be 90 centimeters, at least 100 meters. R plus is 40,000. And the velocity should be limited up to 60 meters per second. We don't want to deal with compressibility effect. And then, of course, we should have the possibility to measure in different sections of the pipe. So this was the requirements. With this specification, that's where these experiments lie. This is a plane where we can see on the x-axis the Reynolds number, on the y-axis the viscous scale. So from what we say, we should, from what we believe, we should be on the right part of this line, on the upper part of this line. So this is what we consider kind of goal area, and we see that Chicope is at least for some of these parameters, is in that. So, but with these experiments, we end up to very large dimensions. We know from the previous talks that actually we need to assure quite high accuracy in the measurements. So we need to be in a place with very low environment contamination, very low electrical noise, very low background disturbances. Moreover, we have to attack the problem with all different types of instrumentation. So this kind of experiment is not easy to install in a single system laboratory. And there is the necessity of a cooperation between university. So that's why few brave guys meet together in an attempt in a cave to use a pipe to hit the cyclop in the eye. So I think this is quite show us what we would like to do. This, of course, is just a preliminary. We see that there are some people that push it a bit more and cooperate, of course, more directly. And there are, of course, a lot of many other groups that support this project in Europe and outside. So where is the site? The site is in Predappio, very close to the second faculty of engineering of the University of Bologna in Forlì. So this is the center of Italy. Predappio is the town where Mussolini was born. So in 1935 he decided, actually it was just a pure agricultural place, so he decided in 1935 to build a factory to increase the airplane production in Italy. This was quite low efficient factory. As you can see, it's wrapped around the mountains, so all the pieces of the airplane were distributed by cables and complicated cable cars. And like in other countries, in order to continue the production during bombing period, he built, in the other side, also where the picture is taken, he built a complex system of tunnels, so to shelter the production and to continue to build airplane during the war. So this is the tunnel complex, this is the entrance. Here we can see this is the entrance, so there is a corridor, and then we have two large tunnels, about 10 meters in diameter and 120 meters length. So these are pictures showing the state of the tunnel. We had a couple of visits from people interested in, first some characteristic of these tunnels. They are located 60 meters underground. There are completely no vibrations. We are far away from any train and road. So it's a very close environment with complete stable condition. The temperature is 16 degrees over here. We did some geological tests, radar measurements. They show that the structure of the concrete is extremely good. And it's a very good condition, and it is almost 2 meters thick. So we had some recognition. You can recognize some of the organizers. So they do not appreciate only the tunnels, but something else. Actually, the picture was taken by Arne Johansson, trying to, this is a long bruschetta, trying to simulate somehow what would have been the experiments. So this is how we decided, where we decided to put the apparatus. Of course, this is a huge area, so we wanted to limit the area that should have been restored. So you can see in red is the facility, in green is the area of the lab. So a first renovation sponsored by the European Community in 2008 started the project. This is how the tunnels were at the beginning. This is how the tunnels are in the present status. So here you can see the second floor. The pipe will be located in this position along this. This is actually the holes that we made in order to put the side of the apparatus. This is the lower floor where there will be the return circuit. Here is here you see what will be the lab, where most of the experiments will be performed. So the final setup of the laboratory is actually will start very soon. We know now the company that will build up all the lab, and we hope it will finish before spring 2011. Meanwhile, we have to agree with this company, and meanwhile, we hope we will be able to start to install also the apparatus. We will have to install all the system outside, the electricity distribution, light, ventilation, cooling system, of course, for the fan, and then the laboratory. That will be made. Here we have to build the pipe. So the pipe is basically a closed wind tunnel. You recognize here a settling chamber with screens and a convergent. Also here you can argue, I mean, that for pipe measurements maybe you don't need such a convergent, you don't need such treatment of the flow in the settling chamber, but we want to be really as much as general as possible. So we want to create a kind of top hat profile at the beginning, and then maybe, of course, we will have the possibility to insert here any type of devices, of grids or whatever. So the main part of the tunnel is the pipe, under the 120 meters length. Then there will be, of course, the return part of the circuit. This strange S, we need to do it because, of course, we need to guarantee the access to the other tunnel, and also we need to guarantee if something happens, the people they should escape. So this part will be actually located below the floor. So this makes the design a little bit more complicated, but we are using some techniques that has been successfully used here in KTH to build a second DL wind tunnel, a small wind tunnel that is here in the lab. The flow will be, there will be a heat exchanger here that will control the temperature of the flow, and then we will have the fan that is driving the flow. The fan is slightly special. It's not like all fan in a wind tunnel, because wind tunnels typically have a very low pressure losses. In this case, the pressure losses are quite high, so we need to use, we use axial fans, but since the pressure losses are high, we need to have multi-stage fan. So just I want, if you have questions, I can show you the different element of the, but just I want to use this last minutes in order to show what will be the element of the pipe. I mean, believe us, we tried many different materials. We didn't want, of course, at the beginning to adapt to carbon fiber. We know that it's extremely expensive. We tried many different materials. We contacted many different companies that they work also with CERN. And actually, we found that to guarantee a deviation in the diameter of less than 1 millimeter is extremely difficult unless you want to build really extremely heavy metal structure. So the carbon fiber seems to be the best compromise in terms of cost and quality. This is how the apparatus will be installed in the tunnel. Here you can see this is the access to the second tunnel and escape, of course. The flow quality, you can see you can regulate the speed with a point. 0.001, so it's 0.01 per meter, and we have a temperature of 0.1 degree control, and of course we have a gradient in the pipe of the temperature, which is limited to 0.25. We are doing together with KTH a lot of works in order to control and damp the sound that will be produced by the fan. These are the final operating condition of the pipe. So at 11 meters per second, we will get an air plus of 13,000, and this is scale of 34 microns, and 38 we have L star of about 12, the one that we used for the design point. Actually, we over-dimensioned the fan in order to arrive to much higher velocity. Of course, well, we will have probably more resolution, but in this case, we can go slightly more up. If I can maybe use 1 or 2 minutes just to finish how it will be used. I think this is important for you, how it will be used. So we will provide a flexible setup for different experiments. You will have the possibility to measure at different stations around the pipe, but you will have also the possibility to mount custom elements that you can produce in your labs. So you will have all the interfaces, so you can come with your own test section and install it wherever wherever you want along the pipe and use your measurement techniques. Okay, so this is just the final schedule that we hope for will not undergo more dilatation. But of course, it's normal for this kind of project. Thank you very much, and apologize for the video. Yeah, it will be about 340 kilowatts, and we need, of course, the same amount of power in order to cool down. So we agreed actually with the Italian electricity provider for 700,000 kilowatts, which cost just by the agreement costed 80,000 euros. Just agreement. Just a signature for that.
So what is your carbon footprint?
As an Italian, let me ask a question that would be nobody else would have the current class. This looks like something like invariant time translation. So is the date you put in the end a reasonable prediction, or should we expect that due to the strange way we organize things sometimes in Italy, to be additional shifts?
No, actually, I mean, the unknown, well, there are still a couple of parameters that might I needed, and it was a nice experiment because I needed lower, I needed to study lower, I needed to study medical stuff. So it's really amazing, but there are still a couple of parameters that can change a little bit, but the main parameter is the one that was fixed just a few months ago. So now the funds are secured, so it's just a matter of, I mean, of course everything can happen, but I hope that most of the things will be now fixed.
But if you have a retirement plan, the system will just place the food.
We have time for one question more.
Unscheduled reason to coming.